Welcome, everyone, to another episode of Vox AI News. I'm Alice.
And I'm John. Today, we're diving deep into an exciting topic that has been making waves in the AI community, flash attention.
Absolutely, John. Flash attention is a new algorithm designed to improve the efficiency of transformers, especially when dealing with long sequences. But before we get into the details, can you give our listeners a brief overview of what transformers are?
Sure. Transformers are a type of neural network architecture that has revolutionized natural language processing and other fields. They use a mechanism called self-attention to weigh the significance of different words in a sequence, allowing them to capture context more effectively.
That's a great start. Now, why is self-attention considered slow and memory-hungry, especially with long sequences?
The self-attention mechanism has a time and memory complexity that scales quadratically with the sequence length. This means that as the length of the input increases, the resource requirements grow significantly, making it challenging to apply transformers to longer texts.
Exactly. And that's where flash attention comes into play. Can you explain what makes flash attention different from other approximate attention methods?
Flash attention introduces an I/O-aware approach, which means it takes into account the memory access patterns between different levels of GPU memory. This is crucial because many existing methods focus on reducing the number of floating point operations, but ignore the overhead from memory access.
That's a key point. So how does flash attention achieve this I/O awareness?
It uses tiling to minimize the number of memory reads and writes between the GPU's high-bandwidth memory and its on-chip SRAM. By doing so, it avoids the need to materialize the large attention matrix, which is a major bottleneck.
Interesting. Can you elaborate on what tiling means in this context?
Sure. Tiling involves breaking down the input sequences into smaller blocks. This allows the algorithm to load these blocks into faster memory, compute the necessary operations, and then write the results back, all while keeping memory accesses to a minimum.
That sounds efficient. What kind of performance improvements have been observed with flash attention compared to standard attention implementations?
Flash attention has demonstrated significant speedups, up to 7.6 times faster on models like GPT-2 and 15% faster on BERT Large compared to previous records. It also allows for longer context lengths, which improves model quality.
Speaking of longer context, how does flash attention enable transformers to handle longer sequences?
By reducing the memory access overhead, flash attention allows models to process sequences that are much longer than what was previously feasible. For instance, it has been used to achieve better-than-chance performance on tasks requiring sequence lengths of 16K and even 64K.
That's impressive. Can you explain the concept of block-sparse attention and how it relates to flash attention?
Block-sparse attention is an extension of flash attention that focuses on only computing the non-zero blocks of the attention matrix. This further reduces the computational load and memory requirements, making it even faster.
So, it seems like both flash attention and block-sparse attention are designed to optimize performance. Can you discuss any specific benchmarks that illustrate their effectiveness?
Certainly. In the long-range arena benchmark, flash attention achieved a 2.4 times speedup over standard attention, and block-sparse flash attention outperformed all known approximate attention methods.
That's fantastic. Now, what are some potential applications of these improvements in attention mechanisms?
The enhancements from flash attention can be applied in various domains, including natural language processing, image classification, and even in tasks requiring long document processing, like legal or medical text analysis.
It sounds like the implications are vast. What challenges do you think lie ahead in implementing these techniques more broadly?
One challenge is that the current implementations require writing low-level CUDA code, which can be complex and not easily transferable across different hardware architectures. There's a need for higher-level abstractions to make these techniques more accessible.
That makes sense. Are there any ongoing efforts to address these challenges?
Yes, researchers are exploring ways to compile high-level deep learning frameworks like PyTorch into optimized CUDA code, which could streamline the process significantly.
That would certainly help. Now, what do you think the future holds for attention mechanisms in general?
I believe we'll see continued innovation in making attention mechanisms more efficient and capable of handling larger datasets and more complex tasks. The focus on I/O awareness could inspire new algorithms beyond just attention.
I completely agree. Before we wrap up, what are some key takeaways from our discussion today?
Key takeaways include the importance of I/O awareness in improving the efficiency of attention mechanisms, the significant speedups achieved with flash attention, and the potential for longer context lengths to enhance model performance.
Well said, John. Thank you for this engaging discussion today. It's clear that flash attention represents a significant advancement in the field of AI.
Thank you, Alice, and thank you to our listeners for tuning in. We hope you found this episode informative and inspiring.
Absolutely. Stay curious and stay informed. We'll catch you on the next episode of Vox AI News.